In this lecture, we will show you how to blow up SPICE. That means SPICE simulator has a convergence problem or it has unrealistic solutions. Convergence problem may be caused by ideal voltage source. For an ideal voltage source, the output is pretty stiff. That means it has the 0 ohm as internal resistance. If the output is short circuit, this voltage source can provide infinite current. The disaster will happen if two ideal voltage sources in parallel with each other. This violates the KVL, which is Kirchhoff's voltage law. In this LTspice simulation, we put two ideal voltage sources in parallel. V1 is the voltage step, V2 is the constant voltage source. If we put V1 in parallel with V2, the error message will pop up in LTspice. To solve this problem, we can simply put a series resistor in between these two voltage sources. Now we can run the simulation. As a result, the current between V1 and V2 is simply defined by the Ohm law. In the second example, we have a voltage step into a capacitor. In this case, it will cause a high current into the ideal capacitor. In the LTspice setup, we choose the rest time as 1 nanosecond, which is unpractical but it's only for simulation purposes. The capacitance is 1 microfarad. According to this equation, the capacitor current is C times dV over dt. That's 1 microfarad times 20 volt over 1 nanosecond, which is 20 kiloamps. That means, in this case, this ideal voltage source will provide 20 kiloamps into this capacitor. Again, this is the ideal case simulation, and it's not practical. We just want to show you that according to this voltage step in green as V in, there's a huge current into the capacitor, which is found as 20 kiloamps by simulation. The solution to reduce the current spike is as follows. First, we can use slower dV over dt, or add ESR into the capacitor, or add series resistor with the voltage source. If we have this high current, this current may cause convergence problem to the rest of the circuits in your simulation. So this may be a problem. Also, the convergence problem may be caused by ideal current source. Ideal current source, that means the output current is pretty safe, and the parallel resistor is infinite, that means it's open. The output voltage can be infinite if the output is open circuit. That means we must avoid open circuit with a current source. If we put two ideal current sources in series, this will violate KCL, the Kirchhoff's current law. In this example, we put two current sources together in series. LTspice will give you the error message as shown here. To solve this problem, we can put a parallel resistor with I1 and I2, the current source, to solve this problem. So we can run the simulation in this case. In this example, it shows a current step into an inductor. In this case, the inductor is very similar like a current source, so we kind of like violate the KCL in this case. This will cause high voltage spike over this ideal inductor. The inductor voltage VL equals to L times di over dt. In this case, it's 20 microhenries times 1 amp per 1 nanosecond, gives you 20 kilovolt over the inductor. This is the training simulation. You can see if we have the current step with 1 nanosecond as the rest time, we will create a 20 kilovolt at inductor voltage. Again, this is unpractical and just for simulation purpose. It just gives you some basic idea about creating some unpractical solutions in SPICE. And this high voltage spike may cause convergence problem to the rest of the circuits. In this example, it gives you a short-term okay but long-term problem simulation. So for example, on the left-hand side, we put a voltage step into an inductor. The inductor equation is given as follows. This is the integer of applied voltage over inductor plus the initial current. So this is the trending simulation. If we put a 1 volt step over the inductor current will be built up and ramp up over time, given a constant slope. This slope is defined by 1 over L, and also defined by the applied voltage, V. On the other side, we have a current step into a capacitor, 20 microfarad. This is the voltage over capacitor is 1 over C times the integer of capacitor current over time plus the initial voltage over the capacitor. In this case, we assume the initial conditions for inductor current and the capacitor voltage are all 0. So we can see the voltage over capacitor will also ramp up over time. For short term, it should be okay, but as time goes by, the values over inductor current and the capacitor voltage will go up and becomes unrealistic. So for short term, this is okay. This is the key point in the design of switch mode power supply. That means the power is transferred from either voltage source to current source or from current source into voltage source in short term. In short term, that means this is high frequency switching, such as a few tens of kilohertz or hundreds of kilohertz. This example shows a simplified simulation model of a switch mode buck converter. Input voltage 10 volt is switched on and off by a switch into a LC filter, which is loaded by resistor R. The simplified version of simulation is shown here. We have a voltage pulse from 0 to 10 volt with duty cycle as 50%. This means it is 10 volt for 50% of period and 0 volt for the rest of 50% of period. The switching frequency is 100 kHz and the period is 10 microseconds. On the left-hand side gives you the transient simulation over time. This figure shows the transient simulation. At the beginning, there's some oscillation, and as time goes by, the system settles down and the output voltage becomes steady state. Transient behavior is caused by the second-order LC resonance. At the steady state, the system settles down, and the output voltage shown on the right-hand side graph is 5 volt, which is 50% times 10 volt, and the output current is simply 5 amps because the load is 1 ohm. Another way to look at this simulation is to use the average model. The average model at Vin is 5 volt, which is 10 volt times duty cycle as 50%, and LC filter during steady state can be simplified short for inductor and open for capacitor. This model can be further simplified as a 5 volt as average voltage into a resistor 1 ohm. It gives you 5 volt at output voltage and 5 amps into the resistor. The power is transferred from voltage source through an inductor as current source and then back to capacitor as a voltage source again. So this is the correct way to transfer the energy, and nothing violates the KVL or KCL. Just in case you have convergence problem in LTspice, which is pretty rare to happen since LTspice is quite robust. Just in case if you have convergence problem, there are 4 parameters can be adjusted in SPICE setup. If you go to SPICE control panel, you will see these 4 parameters. To solve the convergence problem, we can increase these SPICE parameters a little bit. First is the G-min, which is this is a small conductance that is parallel to every node of transistors and diodes. The second one is to increase allowed absolute tolerance. The third one is to increase the allowed relative tolerance. The last one is to add a very small capacitance from each node to the ground. These 4 parameters can be adjusted to solve the training simulation problem. This is the reference I use for the lecture. It's better to take a close look at this reference and gain a deeper insight in SPICE engine. That's all done for this lecture. Thank you very much.